Hey, everybody. Hope you're all doing well. Haven't seen you for a little while. It's been kind of a crazy week, huh? Well, I think maybe we have a new president. We'll see. See how it all plays out. But other than that, we are just a sliver behind, not really behind, but just, a sliver. So we're going to play catch up today. Let's go ahead and look at our syllabus together, just so we're all on the same page. I'll pull it up here. Where are you? 130. There we are. Okay. So we're sitting right here at acids and bases equilibrium. We've got some more solution stuff to do. So we'll see how this plays out. If I need to push this test back, I will. I'm not committing to that just yet though. All right, so let's see how it goes. So pulling up chapter 9, we left off, we were talking about concentrations, and the different ways that we can express concentration. So we had, we were messing around with mass percent, right? Jordan, was that where we left off? I can only see your face. So yeah, okay, cool. So we were messing around with mass percent. You take the mass of the solute divided by the mass of the whole solution to get your value. So here we've got a solution is prepared by mixing 15 grams of Na2CO3 and 235 grams of water. Calculate the mass percent. So we would take the 15 grams and divide it by 15 plus the 235. All right, so both of those two components added together to give us 6%. So now we've got this thing called volume percent. So similar in setup to mass percent, except instead of using grams, we're going to use milliliters. So we'll use milliliters of solute over milliliters of solution. This one works really well when we're dissolving a liquid in a liquid. Another way we can write our volume percent, if we're given a value, is that it's the milliliters of the solute over 100 milliliters of solution. We also have a mass volume percent. So this is sort of combining the last two. So we take mass on top, so grams of solute on top. This one works well if we are dealing with a solid dissolved in a liquid. Okay, so grams will go on top, and then on bottom will be milliliters of solution. Remember that it's milliliters and not liters, all right? And then we multiply by 100 to get us into that percentage value. So we can think about these different values as conversion factors. Because if it's a percent, that's meaning that it's per 100. So when I say that I have an 8.5% mass NaOH solution, that's the same thing as saying, because it's 8.5, I know that's 8 point, oof, that's bad. A little more space here. That is the same thing as saying 8.50 grams of the solute, and in this case it's NaOH, over, it's a mass, so over 100 grams of solution. All right, so those two things say the same thing because a percentage is per 100. If we look at this one here, B, so this is A, we look at B, B is a volume percent of ethanol. So this is also saying 5.75 milliliters of ethanol for every, how many? 100 milliliters of solution. So if you happen to be writing these guys as conversion factors, which you can do, it'll always be per 100. C down here, this is a mass volume percent. So if it's 4.8 mass volume, that means it's 4.8 grams of hydrochloric acid, HCl, in every, what is it? 100 grams of solution. Okay, so notice the 100 will go on the bottom. So you can go from this percent value into a conversion factor. Great. And then you can write them either way, okay, depending on how you want to use them. So you could put the 100 grams on bottom or the 100 grams on top, depending on which value you want to go to and from. So I want to do an example of those before we go into molarity. So given we have a solution that let's say it's has a mass volume percent of 33%, okay? You also know it's mass. Mass of solute is equal to 6.3 grams. Okay, I want you to find volume of solution. And let's say this is a hydrochloric acid solution. So mass of solute, it's 6.3 grams of HCl. So if I'm going to figure out the volume, all right, you could just plug it into the equation, which says there's two different ways. So the equation is that mass volume percent equals your mass of solute divided by your milliliters of solution times 100. And so we could plug our values in. I can plug the 33 in here. I could plug the 6.3 in here and then solve from there. Another way is to use this 33% as a conversion factor. So it's a mass volume percent. So that's the same thing as saying I have 33 grams of HCl in every 100 milliliters of solution. So if I start with my given information, which says I have 6.3 grams of HCl, and we use this as our conversion factor, I wouldn't want to use it like this, right? Grams is on the top here. I want to flip-flop those. So for every 100 milliliters of solution, I know that I get 33 grams of solution. Now, if I plug this into my calculator, we're going to take the 6.3 times 100 divided by 33, and we end up with 19.1, let's go with only two sig figs, 19.1 milliliters. Now, if you've taken chem recently and you used it more like in this equation, let's do that as well. It should give you the same answer, okay? So if I plug it in using this, I've got my mass percent is what, 33%, and it's gonna equal my 6.3 grams times my milliliters, which I'm trying to find. This is what I'm trying to find, times 100. So going through this process, I'll divide by 100 on each side, divide by 100. What I end up getting is 0.33 is equal to 6.3 grams over my milliliters. I want to find milliliters. So I need to move milliliters to this side and the 0.33 over to this side. So I'm going to multiply this side by milliliters, because then it'll cancel. I'm going to multiply this side by milliliters. All right. Then I need to get rid of this because I want milliliters by itself. So I'm going to divide this side by 0.33, divide this side by 0.33, and we take our 6.3 divided by 0.33, and our milliliters should equal, all right, if I take 6.3 divided by 0.33, 6.3 divided by 0.33, and I end up with 19.1 milliliters. Okay, so either way, either plugging it into the equation or using it as a conversion factor is going to give you the same value. So let me give you one. To do on your own before we go to molarity. So how many grams of KCl are in 185 milliliters of a 2.56 mass volume percent solution? All right, I want you to go ahead and work on that. You can go at it either way. So if you like plugging it into the equation, plug it in. If you'd rather do it with a conversion factor, that's fine too. I'll give you all 3 minutes. All right, so for this one, again, we can go at it 2 different ways. I'm going to use this as a conversion factor. So if I have 2.56 mass volume percent, that's the same thing as saying that I have 2.56 grams of, and in this case, it's KCl, in every 100 milliliters of solution. Okay, so this becomes a conversion factor. I start with my given. So I have 185 milliliters. 185 milliliters of my solution. And I want to know something about grams. So I'm going to use this thing here, and I actually can plug it in this way. The milliliters can go on the bottom. And the gram value will go on the top, 2.56 grams of KCl. The milliliters will cancel and we'll be left with just grams. And 185 times the 2.56, divide that by 100, and we end up with 4.74 grams of the KCl. Any questions? You do have one, you can throw it in the chat. So there's one last type of concentration that we talk about, and that is molarity. And that one's really common. We'll see it a lot. If you're working in a lab setting, you'll see it a lot. So molarity is talking about moles of solute per liters of solution, okay? So molarity equals moles of solute over liters of solution. There is no multiply by 100 because molarity isn't a percentage value. So don't add the times 100 for this one. Moles are not usually a value that's given. A lot of times you'll be given information in grams. So make sure you convert your grams into moles. And then also note that it's liters of solution. So the last couple things we had talked about were in milliliters. This one is in liters. So if I say something like, I have 1 molar solution, and this is how you'll always see solutions in the lab setting, it'll have this big M value, capital M. That isn't meters. It's not moles, it's molarity. Molarity is not the same thing as moles. It's related to moles, but it's not the same thing. So if I said that I had a 1 molar solution of NaCl, that's the same thing as saying that I have 1 mole of NaCl for every 1 liter of solution. The number that you have here always corresponds to the mole value. So let's change this. And instead of saying I have 1 molar solution, say I have a 6 molar solution. Okay, so if I have a 6.0 big M solution of NaCl, that is like saying I have 6 moles of NaCl in every 1 liter of solution. All right, it's always per liter. If I had 3.52 molarity, it would be 3.52 moles of the NaCl for every 1 liter of solution. Okay, so always pair that number with your top value if you're trying to get it into a conversion factor. So I would say molarity is probably the most common way that we measure concentration in chemistry. So let's look at this one here. It says, what is the molarity of 5 liters of an NaOH solution if it contains 6 grams of NaOH? I'm going to rewrite this on my whiteboard. So we've got 5 milliliters of NaOH, So our given information here is we have 0.500 liters of an NaOH solution. And we also know that we have 6.00 grams of NaOH. 6.00 grams of NaOH. And we want to find molarity. So right off the bat, I'm just going to write my equation. Molarity equals moles over liters. So I need a mole value and I need a liter value. Well, look it up here. I have a liter value. Awesome. So I can actually just plug that right in. So my bottom value in this equation is going to be the 0.500 liters. My top value is in moles. What am I given? I'm given a value in grams. So the first thing I need to do is convert the amount of NaOH into moles. So 6.00 grams of NaOH. To convert it into moles, 1 mole of NaOH equals, I'm going to cheat and look at the slides because I don't want to, 40 grams. Yeah. All right, so 40.00 grams of NaOH. Where is this number coming from? I'm taking the weight of 1 sodium, 1 oxygen, and 1 hydrogen. So from here, we convert into a mole value, and that's what we'll plug into the equation. So 6.00 divided by our 40, we get 0.15 moles of the NaOH. So we'll just plug that back in here, 1.50 moles. And divide that out by 0.5. And we get 0.3, let's go with 2 sig figs, 3 sig figs rather, 0, 0. And the unit on this is capital M, big M. Another way to write this, let's say we were to solve for another problem. So another way to write this thing is to say I have 0.300 moles for every 1 liter. And why don't we use that? Let's use this thing right here. Let's say, we'll tag on. You have 15.6 liters of the above solution. How many grams of NaOH do you have? So I'm going to give you 4 minutes just to try and play around with that. See if you can make that happen. Let's add what the molarity is. We said it was 0.300 big M. Okay, so you can come up with the grams. Okay, so to mess around with this one, again, you can just plug it into the equation. So if you like the idea of going, well, molarity equals moles over liter, and I know molarity and I know my liter, so I can solve for moles and then convert to grams. You can do that. I'm gonna write this as a conversion factor though. 0.300, and this means moles over every 1 liter of solution. And it's specifically moles of the solute NaOH. So I start with my given information, which is 15.6 liters. So I have 15.6 liters of solution. And I can use my conversion factor here that says 0.300 moles of NaOH for every 1 liter of solution. Now the problem doesn't want it in liters, it wants it in grams. So I'm going to convert this back into grams. For every 1 mole of NaOH, it's roughly 40.00 grams of NaOH. The moles will cancel, the liters will cancel. If you did this problem and you stopped here and then you solved this after the fact, that's okay. I just chained them together. So 15.6 times the 0.3 times the 40 divided by 1. Okay, so we should end up with 187 grams of our NaOH. Any questions with that problem? What's happening with molarity? Okay, here's one that I want you to do. So this is asking you to calculate the molarity. So what is the molarity if you have 0.225 liters of KNO3, solution containing 34.8 grams of KNO3? Okay, so for this one, we want to solve for molarity. So remember, molarity equals moles over liter. We've got a liter value. Awesome. We have a gram value. So I need to convert grams into moles first. So we'll take the 34.8 grams and divide it by the molar mass of the KNO3. And the molar mass of your KNO3 should be 101.11, 1 potassium, 1 nitrogen, 3 oxygens. What we end up getting is 0.344 moles of the KNO3. Once you have the mole value, then you can just go ahead and divide it by the liters, right? Because moles over liters is your molarity concentration. So when we take our moles and we divide it by our liters, we end up with 1.53 big M. And what I see happen a lot of times with students is they get this big M mixed up with moles. So just moles is MOL, right? Lowercase MOL. Big M is talking about moles per liter. Molarity is a conversion factor. So yeah, if we have something that says 3.5 molarity, it's the same thing as saying 1 liter is equal to 3.5 moles, or we can write it either way. We've already talked about that. So I don't want to do that one because we already worked on that. I'll do that one. I do want to do this one. Okay. How many grams of AlCl3 are needed to prepare 125 milliliters, hint, hint, wink, wink, milliliters of a 0.150 molar solution? And so you guys have, I'll give you about 4 or 5 minutes to do this one. All right, so in this one, remember how many grams? So we want to find grams of AlCl3. Now, if I'm dealing with molarity, anytime I see the symbol for molarity, I just kind of am like, all right, molarity equals moles over liters. I won't be able to get grams directly. I'll be able to get moles. I'm cool with that. And I won't be able to get liters. I need milliliters, or I'm given milliliters and I need it in liters. So this is my given piece of information. This thing I can also write like this: 0.150 moles in every 1 liter. So when plugging this in, I start with my given information. I have 125 milliliters, but I don't want it in milliliters. I want it in liters. So for every 1 liter, I get 1,000 milliliters. That will cancel there. And then I can use this relationship here that says, hey, for every 1 liter, I get 0.150 moles. And then from there, for every 1 mole of this AlCl3, so aluminum chloride, its molar mass is going to be 133.3. Okay. Now, if you broke it up, if first you were like, oh, I see that this is in milliliters, I need it in liters, and first I'm going to solve for that. Then I'm going to plug it in. Then I'm going to convert it back. That's fine. No problem there. I just sort of like to string it together. All right, I got 2.499, so 2.5 grams of the AlCl3 should be the answer that we get for that. If we look at the way they have it solved, first they told us, hey, our relationship with the conversion factor and then our molar mass. Right, they converted it into liters. I did that first, but they have it just sort of starting with this already in liters, converted it into moles. Converted it into moles, and then from there converted it back into grams. So next thing we're going to talk about is dilutions of solutions. So if you ever had that, like, I really don't like that kind of orange juice, but if you've ever had that kind of orange juice where it comes in a can and then you have to dilute it with water, you can think of the concentrated amount as the solute, and then the water is the solution. So you dilute it by 3 cans. If I have 1 can of orange juice and 3 cans of water, that'll give me 4 cans of this, or 1 can of the orange juice concentrate. 3 cans of water will give me 4 cans of the orange juice. So we increase the volume, but we decrease the concentration, right? If you were to drink this, it would be really, really sweet, but there isn't a whole big volume. Here, as we increase the volume by diluting it, we're going to decrease the level of sweetness because we're diluting it. So in a dilution, water is added, the volume of the solution will increase, the concentration will decrease. So volume and concentration will be inversely related here. It means as one goes up, the other goes down. Mass of the solute in the solution will remain the same. So the amount of orange juice, or the amount of orange juice concentrate, doesn't actually change, we just dilute it. It's just being distributed out through a larger volume. So because of these factors, we can actually come up with a really simple equation for diluting materials, figuring out how much we need. And it's this right here. So M1V1 equals M2V2. Sometimes you'll see it as C1V1 equals C2V2, the C being concentration. Here, M is just the molarity. Molarity is a type of concentration. So either one of those will work. But the initial concentration times the initial volume will always equal the final concentration times the final volume. And if this is sparking like traumatizing memories of solution stoichiometry from a while ago. You don't have to do solution stoichiometry in this class, all right? This is the only thing we'll have to do. So pretty easy equation. So how do we work with this? Well, how many variables do we have? 1, 2, 3, 4. So 4 variables. I'll give you 3 of the 4. You do want to make sure that your values are the same. So if your concentration is in molarity here, it needs to be in molarity here. If your volume is in liters, the other volume needs to be in liters as well. Thanks, Ashley, for letting me know. Okay, so we prepare a table of the concentrations and the volumes, rearrange the equations so that we can solve for the unknown. Let's look at one. What is the final concentration when 0.5 liters of a 6.0 molar HCl solution is diluted to a final volume of 1 liter? Anytime you see the word dilute or diluting, you're going to want to use this equation M1 V1 equals M2 V2. M1 V1 equals M2 2. U M2 V2. The ones, this is going to be your more concentrated thing. Okay, so maybe give yourself a little reminder, more concentrated. The twos are going to be your less concentrated. So in this case, it's asking about the final. It says we're starting with this. So this is a 6 molar. This is a higher concentration. This is a lower volume. So this is my M1 V1 stuff. This here, the final volume, bigger volume, that's where we're headed towards. This is my V2. You want to be able to distinct those. You don't want to mix your M1s and your V2s together. So looking here, we've got our equation, M1 V1 equals M2 V2. We want to solve for M2. We're trying to find the final concentration. So if I solve for this one, M2, I need to get it by itself. So I'm going to divide by V2 and divide by V2, right? The V2s will cancel. And we come up with this equation here that M2 equals M1 times V1 over V2. And it's just as simple as plugging it in the equation. So my initial concentration is this here. So we put that in. My initial volume, right? Because we want our initial volume is this here. My final volume is the more diluted thing that goes on the bottom. And what do I end up with? 3 molar HCl concentration. Did I become less concentrated? I was at 6, now I'm at 3. Yes, we actually did in fact dilute it. And if you look, how did this change here? We doubled this, so we halved this. So go ahead and figure this one out here. What volume of a 2% mass volume HCl solution can be prepared by diluting 25 milliliters of a 14 mass volume HCl solution? I'll help you out. You will want to use M1 V1. No, not M1 because we're not dealing with molarity. C1 V1 equals C2 V2. So figure out what your C's and your V's are. Go from there. All right, so I think that the hardest part with this is just figuring out which one is the C1, which one is the V1. So in this case, C1, V1, C2, V2. So what volume of a 2% mass volume HCl solution can be prepared? So this is the final stuff. This is talking about my final stuff. Another thing that confirms that can be prepared by diluting 25 milliliters of a 14% mass volume solution. So remember, the 14% is a higher concentration than the 2%. Our C1 is always going to be the higher concentration. So I'm going to put this as my 14.0%. So my second concentration, I'm trying to dilute it down to 2%. So I'm trying to dilute it by like 7 times. My initial volume is 25.0 milliliters. So I'm trying to figure out what this V2 is. V2 will equal my C1. It's not looking like a subscript. C1, V1 divided by C2. Move the C2 over. So my C1 is 14.00. Is it just 10 here? 14.0 times my V1, my initial volume is 25.0 milliliters, and you can keep it in milliliters, that's fine, over my 2.00 mass volume percent. So I take my 14 divided by 2, which is going to be a factor of 10, right? So my concentration is going down by a factor of 10, or 7, sorry. 14 divided by 2 is 7. So my concentration is going down by a factor of 7, which means my volume should go up by a factor of 7. So I take that 7 times the 25, and I end up with a V2 of 175 milliliters. Let's see how they did it. Should be the same. 175 milliliters. Okay, if the problem explicitly asks for it in liters, convert it to liters. Always looking for those little details. Sure, why not? We'll do one more. What is the mass volume percent of a solution prepared by diluting? We've got 10 milliliters of a 9 mass volume percent NaOH solution to 60 milliliters. So we're taking it from 10 and we're diluting it to 60. I'll give you just 2 minutes for that. Okay, so in this one, we're going to use C1 V1 equals C2 V2. We're trying to solve for C2, or the final concentration. All right, if I'm going from 10 milliliters to 60 milliliters, I'm increasing the volume, which means I'm going to decrease the concentration, right? This is increasing by a factor of 6, so this should decrease by a factor of 6. When we plug it into our equation, we get C2 is equal to my initial concentration times 10 over 60, or this 1 to 6 value, or we get 1.5%. The concentration that it pops out should be the same units as the concentration that you started with. All right, I think that's enough for those. So a couple other things I want to talk about, properties of solutions. So solutions in general are transparent. They won't separate. So if I have a salt solution, you know, it's not like sand and water where I shake it up and then if I put it on the table, it'll settle out. The material, the solute, should remain suspended in solution. It can contain small particles, ions, or molecules that cannot be filtered through a semi-permeable membrane. So if I was to take my salt water, which is our kind of standard solution, and pass it through a filter paper, like a coffee filter, I'm not going to collect any of the salt. The salt will move through as well. We have these things called colloids. So colloids are a little bit different than our solutions. They have a medium-sized particle, so the particles are a little bit bigger. They cannot be filtered, all right, so they won't go through the filter paper, but they can be separated by a semi-permeable membrane. So whereas in a solution, our small particles are not, a colloid will have particles that are big enough to get trapped by a semi-permeable membrane. So some examples of colloids: fog, clouds, hairspray, dust and smoke, shaving cream, styrofoam, marshmallows. These are all things where we could actually separate out the solute from the solvent. Big one that we see, blood plasma. Okay, we can separate those out. Then we have things called suspensions. These are heterogeneous, non-uniform mixtures. So heterogeneous from the very beginning of the semester, they're not evenly mixed throughout. These are really large particles that can be filtered through paper, through a filter paper. They have to be stirred to stay suspended. So this suspensions is that idea of like sand and water, or clay and water, or muddy water, or even like blood platelets. They have to be circulating or moving in order for them to stay suspended. When you have, you know, the French Broad, when there's a lot of rain, it tends to get muddier because all of those small clay particles are suspended. When it's haven't had rain for a while and it's moving slower, those suspensions are able to fall out. So solutions, colloids, and suspensions, you definitely know the difference between those, what can and can't filter them out. Right. So a mixture that has a solute, particles that do not settle out but are too large to pass through a semi-permeable membrane would be considered be a colloid. So that's our middle guy, right? The solution, it will stay in, and it this one is our kind of, you can't take it out in any way. This one you can separate it out with the semi-permeable. The suspension will fall down as well. So based off of all these things, we have this process called osmosis. So in osmosis, water solvent flows from a lower to a higher solute concentration. So if I put a semi-permeable membrane in a beaker, I separate these two sections, but they're not separated by a piece of glass. They're separated by a semi-permeable membrane, meaning that certain things can get filtered out. If one side is water and the other side is water with sugar, well, osmosis will tell us that water is going to flow from a lower concentration to a higher concentration environment. So in this case, water will flow from left to right. And there is some water flowing from right to left, but it's not as great as what's flowing from left to right. Or what happens is the diluted thing wants to dilute the more concentrated thing until the concentrations become equal. So the level of the solution with the higher concentration will rise. So we would expect to see the water level here increase, or it will be higher than what we have on the lower concentration. They want to equal out. So we have this thing called osmotic pressure, and this is equal to the pressure that would prevent the flow of additional water into more concentrated solutions. It's greater as the number of dissolved particles in the solution increases. So if I have my water flowing from here over here, because the water is wanting to sort of dilute this side, if I tried to resist or stop this water from flowing, that's known as osmotic pressure. The more particles we have on this side, the more concentrated it is, the more intense that flow is going to be, the greater the pressure is going to be to stop it. There's a process known as reverse osmosis. So a pressure greater than the osmotic pressure is applied to a solution, which will force the water in the opposite direction, purifying the solution. Now what I can do is I can apply some sort of energy or pressure to this side of the material, and I can force the water to go back. But if I force the water through, the little sugars aren't going to come with it. So we purify the water by pushing the water through, leaving the sugar behind. Sometimes people talk about doing something like this for desalinization. We have salt water, we have pure water. We force the salt water through a membrane. The salt is left behind, and we have pure water over here. Why is that not a very widely used thing? Because it requires a lot of energy to overcome the osmotic pressure, or reverse osmosis requires a lot of fossil fuels. So this idea of osmosis and osmotic pressure is really useful when talking about blood cells, because the lining of our blood cells is a semi-permeable membrane. Okay. When we have a solution that's called isotonic, isotonic means that the solution on the outside has the same concentration as the solution on the inside. So if we think of our water or our blood cell as, and around that is the semi-permeable membrane. If I put it in a solution that's isotonic, these are the values for isotonic solutions. You do need to know these or have them referenced somewhere. So a 5% mass volume glucose would be considered isotonic, and a 0.90 mass percent or mass volume NaCl solution is considered isotonic. So this is the concentration that we find in our blood cells. If the water or the solution outside of it also has those concentrations, the water flowing in and the water flowing out will be equal. What do we expect to happen to our red blood cells in this case? Nothing. They're healthy. They're happy. Okay. So we'd like to keep the solution around our blood cells isotonic. Now let's talk about what happens if we start fiddling with this outer solution. So what if we have a hypotonic solution? In a hypotonic solution, the solution on the outside has a lower concentration of sugar and salt than our blood cell itself. What do we remember about lower concentration? Okay, so I'm going to even write it in here. Low concentration in the blood cell is got a higher concentration. Where does water flow? Water likes to flow in the semi-permeable membrane. Water wants to flow from low to high. It wants to dilute the blood cell. So if water is rushing into our blood cells, we will go through a process known as hemolysis. This is not good, okay? Hypertonic solutions will cause the blood cells to swell. And in some instances, the blood cells can burst. So if you get into a situation where maybe you don't have enough sugar in the solution around your blood cells, or you don't have enough salt in the solution around your blood cells, you can actually burst your blood cells. What about if we go in the opposite direction? So instead of a hypo, and like hypo, under or low, what if we have a hypertonic solution? So in a hypertonic solution, we have a super salty solution, all right? So this is a high concentration on the outside. High concentration. So our blood cells have a relatively low concentration. Let's say we haven't been drinking enough water, all right? And our body is really salty, okay? The water from the blood cell is gonna flow out into the solution, and we're gonna dry out our blood cells. This is known as crenation, shrinking of the red blood cells. This is not good either. So what we want to do is keep a solution that is roughly 5% mass volume sucrose, which is sugar, and 0.9 mass volume percent salt. You do want to know these relationships. I'm not going to get into dialysis, but let's look at this. Okay. Indicate whether each of the following solutions is isotonic, hypertonic, or hypotonic. And I'm talking in reference to blood cells, okay, to red blood cells. So we're talking in reference to red blood cells. So go through these and tell me what you think. Okay, so if it's a red blood cell, we like to have 5% glucose, and we like to have 0.9% sodium chloride. So if I have a solution that's 2% sodium chloride, is that greater, the same, or less than what we like? In this case, it is greater. It's over twice as much. So we're going to say that this is a hypertonic solution. C, too much salt in the solution. What about this one here? We have a 1% glucose solution. Okay, we want to have 5% to keep it isotonic, but it's too low. So this is going to be a hypotonic solution, too low, not enough sugar in the solution. If I have 0.5% NaCl, that is too low, right? I want it to be 0.9%, and it's only at 0.5. So this is also a hypotonic solution. What if I have 5% glucose? That's the magic happy place for our blood cell. That's isotonic. So we're going to give that an A. That's where the water flowing in is equal and opposite to the water flowing out. So our cells would be happy there. Let's see what happens to the actual cells themselves. So when placed in each of the following solutions, indicate what happens to the blood cell. So I'm not asking about the solution now, I'm saying, what does the blood cell do? So remember, red blood cells, they like 5% glucose and 0.9% NaCl. So if we drop a blood cell into 5% glucose, what will happen to the cell? Does it expand? And hemolysis is when it expands. Crenation is when it shrinks. So what will happen in 5%? 5% is our happy place. So we shouldn't expect any change at all. All right, so I'm going to put A there. What if we're in a 1% glucose solution? I'm going to draw this out because it always seems, I get confused on these. So I'm going to draw a little beaker. I'm going to put my red blood cell in there. This has a 5%. And we're saying that our solution is 1%. So we always go from, the water is going to flow from low concentration to high concentration. So in this instance, my water is going to, because it's trying to dilute the higher concentrated thing, my water is going to flow from the outside into the red blood cell. If I'm going into the red blood cell, that's hemolysis. We're going to expand or pop our blood cells. What about 0.5 NaCl? Okay, so I've got my beaker again, a little bit bigger. I've got my blood cell. My blood cell likes to be at 0.9%. The solution is at 0.5%. So in this instance, the solution around it is lower concentrated than the solution in the cell. So this is sort of like what happened before. Lower concentration water will flow to higher concentration to try and dilute or balance those out. So we're flowing into the cell. If water is flowing into the cell, hemolysis or expansion, B. Last one here, instead of it being 0.5 around, let's change that to 2%. Very, very concentrated, super salty. Well, water is going to want to flow from the lower concentration to the higher concentration, or water is going to flow out of the cell. In that case, we're going to undergo crenation or shrinking of the shell, the red blood cell. Questions on that? Yes, no, maybe so? No? Okay. You do want to know the blood cell values? I may ask you, hey, if I drop this in this solution, would it expand or contract? Things like that. Okay, we're done with that chapter. I got like 3 minutes. I'm going to start acids and bases if I can. So acids and bases and equilibrium. This goes along with solutions because acids and bases tend to be brought into a chemical reaction in a solution. So the term for acid, its Latin root is sour. A lot of things that are sour, have a sour flavor to them, are acidic. Same thing with like vinegar. Lots of acidic foods have that soury taste. So there's a couple different ways that we can classify acids. The most simple way that we can classify something as an acid is under the Arrhenius definition. And under the Arrhenius definition of an acid, or an Arrhenius acid, it is going to be a material that when I drop it in water, it's going to break apart and we're going to get H pluses. So when I see HCl, if I drop it into water, it's going to break apart into H pluses and Cl minuses. This production of H plus is an electrolyte, is what makes it an acid. A couple other properties: it'll have a sour taste, it'll turn blue litmus paper red, and it tends to corrode metals. Okay, acids will corrode metals. As far as naming acids are concerned, acids will have an H in the front and it'll have some sort of nonmetal. The nonmetal could be either a polyatomic ion, or it could be just a binary acid with one other material. If it's one other material like this, we call this hydrochloric acid. We ick the root of the second name. If it happens to be a polyatomic ion like this, ates turn to ick and ites turn to us. So this is chlorate. So if I was to make it an acid, it would be chloric acid. I don't use the hydro with a polyatomic. Okay, I ate something icky. Kind of already gone over this in nomenclature, but ite goes to us. So if I had this polyatomic ion here, this is chlorite. I drop the ITE, I change ite to us. So it becomes chlorous acid. Here's a bunch of different acids. So we've got hydrochloric acid, hydrobromic, hydroiodic. This is hydrocyanic acid. And then we start, this is the one polyatomic ion that we actually use the hydro for. All these other ones, you'll see we don't use hydro with the polyatomics. Okay, so for this guy here, select the correct name. This is hydrogen with just one other thing. So this will use hydro. We like hydro. So hydrobromic acid. Here we've got hydrogen mixed with a polyatomic ion. So I'm going to ditch the hydro and we're just going to look at the polyatomic ion. That's carbonate. Ate becomes ick. I ate something icky. So this would be carbonic acid. This last one here, sorry, this is, where am I? There we go. This is hydrogen mixed with bromite. Bromite, ITE, ite becomes us. So we would call this bromous acid. An Arrhenius base, also a very simple definition, says that anything that I stick into water and I get an OH minus or a hydroxide ion, that is a base. So H pluses are an acidic thing, OH minus are a basic thing. NaOH, sodium hydroxide. When I drop this into water, I get sodium and I get hydroxide ions. Hydroxide ions are what give it a basic quality. Bases have a bitter taste or a chalky taste. We don't usually eat basic things. They tend to taste kind of icky to human beings. That's because they contain a lot of poisons. Okay, not all basic things are poisonous, but a lot of basic things out in nature have a kind of ugh taste to them. They also will feel soapy or slippery. A lot of cleaning supplies like bleach and stuff are bases. And they'll turn litmus paper, indicator paper blue, and phenolphthalein indicator pink. That I don't care as much about, the indicator papers. So here are some bases. Sodium hydroxide, all right? We've got the name of the metal and then the polyatomic ion. Potassium hydroxide, barium hydroxide, aluminum hydroxide. All of these hydroxides are giving us the OH. So we're gonna leave it there. We'll come back on Wednesday and finish up acids and bases. If you have any questions, feel free to stay around. Otherwise, I will see you all on Wednesday. Enjoy the rest of your week.